So the final chapter we need to learn about is electrical power. So as you can see, these all use electricity. The light bulb uses electricity as well. So let's have a look. Electrical energy is converted by appliances in the home into other forms of energy. A radiator converts electrical energy into heat energy. An electric light converts electrical energy into light energy. And the TV converts electrical energy into light as well as sound energy. So in these different types of appliances, basically electricity goes in and then changes into something else that's useful. Or sometimes not useful as well. We'll have a look at it. The rate at which this energy conversion takes place is the appliance is the power of the appliance. So the rate at which this energy conversion takes place is basically what the power is. So I'd write that down. So power is the rate of change of energy or the rate at which the work is done. So I'll probably highlight that or copy it down in your PowerPoint slides. And power P is given by, let me just get rid of these, this little equation. W is work done in joules, it's energy, divided by time in seconds. So I would copy that down in your equation sheet. P equals W over T. Time should already be there. Work, I think, should already be in there. Chuck it in if it's not in your topic 2 equation sheet. And P is power. So let's keep looking into it. So power is the rate at which energy is transformed by a circuit component. Power P is the rate at which energy is transformed and is calculated using the formula below. So also, we can see that we use W over T, but we can also use delta E over T. So P can also be delta E over T. So now units for power is watts. So this is what you write in the units column, which is equal to 1 joule of energy being transformed each second. So it's 1 joule per second. So these are some examples. If an appliance is operating at a power of 1 watt, so that's the power, then what it means is it's converting 1 joule of energy per second to other forms of energy. So that's the power of the appliance. A kilowatt is equal to 1,000 watts because kilo is 1,000. An appliance with a power rating of 1 kilowatts would convert 1,000 joules of electrical energy into other forms of energy each second. So kilowatt is more powerful than 1 watt because that's just more power. More energy is getting converted. Every appliance has a stated power rating. A laptop has a very low power rating, typically at about 80 watts. But a reverse cycle air conditioner has high power rating, typically 2,000 watts. So those are just some examples. So let's have a look at this example. It tells you to calculate the power of a microwave. So my facts would be P is question mark, which transforms 51 kilojoules of energy in, I can't see because I'm recording, in something seconds. I'll show the facts because there's a little thing while I'm recording. So 30 seconds, time is 30 seconds, my energy is 51 kilojoules, which kilo is 10 to the power of 3, so I just replaced K with the 10 to the power of 3. Hopefully you're a bit used to that now. So P is what we're trying to find. Now, what was the equation that we used? That's on your equation sheet. It should be P equals delta E over T. All you have to do is sub those values in and chuck it in your calculator and you get about 1700 watts. So a microwave, this particular microwave, has a power of 1700 watts. Right, have a look at these different appliances over here. These are just some average typical power ratings. So a fluorescent tube, about 40 watts, 40-inch LED television, 150 watts, electric drill, 300 watts, reverse cycle air conditioner, 2,500 watts, laptop 80 watts, microwave about 1,000 watts. Now you can also see a physical activity, a typical power rating of a person. So sleeping is 75 watts, walking is 300 watts, and running is 600 watts. So obviously you can see that when you're sleeping you're not using that much energy, so there's less power. You're not using as much when you're walking compared to running, so there's less power. So a power consumption of an appliance is found in different quantities. The potential difference across the appliance, which is difference, so it's V. The higher the potential difference, the greater the amount of energy each charge carries converts into other form of energy, because there's more supply. Basically, the battery supplies more energy, so there's going to be more power. So the current through the appliance, I, the higher the current, the more charge carriers pass through the appliance. Since each unit of charge carries some energy, the more charge per second or current, the greater the power. So basically, using those two information, we understand that for this one, P is proportional to V, P is also proportional to I. So you can actually put it into an equation. P equals VI. So power, we've already had two equations that equals power. We can create another equation. P equals VI. So write that in your equation sheet. V, we already know it's a potential difference. I, we already know it's the current. So copy that down. So, deriving alternative electrical power formula. So we started off, remember, with P equals W over T, work done over T. And since my V voltage is W over Q, and work done is VQ if I rearrange this equation, so that equation just turns into that. So basically, if I just put the VQ in here, it just becomes power equals VQ over T. But from our equation sheet, hopefully you remember that I is Q over T. So this just simply gets replaced by I. So that's how you derive it. So you begin with power equals work done over time, and then hopefully you remember that the potential difference is work done over per charge as well. So you rearrange that equation, substitute it into the work done, so you get P equals Q, this one, VQ over T, and then you realize Q over T, well, that's just current. So I replace it, so I get P equals VI. So that's how I get that third equation. Okay, so hopefully that's P equals VI is copied down as well. This is just how you derive it. Right, electrical power is the rate at which electrical energy is transformed by a component or load in an electric circuit as it's calculated using the formula below. So we've got P equals VI, remember that's the third equation, and V can also be written as delta E over delta Q, and I can also be written as Q over T. So that's how we convert this one into this second equation we learned. Now, there's another equation we can use, and you can use Ohm's law to derive something else as well. So we know that P equals VI, that was a, remember, third equation we learnt. And we also know that delta V using Ohm's law is IR. So I've replaced it with IR. I've got my current here, so it becomes I squared. So I can also, so a fourth equation, I can also write power as I squared R. So power has multiple different equations. I know you've written all of it, but why not make a summary one at the end? P can be work done over time. P can also be change of energy over time. P can also be the potential difference times current. It can also be current squared times resistance. So those are all 4 different equations you can actually use to calculate power. So copy that down. So let's have a look at this example. Unfortunately, again, I can't see the whole question because it's my recording device is on the question. So let's just go straight to the facts. V is 240 volts and my current is 10 amps. So what is the power? Well, hopefully you can see which equation should I use. Let's have a look. It has a V and an I. So I'm going to use this one. So that's how you have a look at it. Write down all the facts first and then figure out what equation you will use. So this is the equation you're going to use. P equals delta V times I. Chuck in your values and you get to go. 2,400 watts. Right, what about this one? Now make sure you do pause the video and copy it when you need to, guys. Your PowerPoint slides should be fully finished. A globe has stamped on it 240 volts and 60 watts. Find the current that will pass through the globe and the resistance of the lamp when operating at this current. So I've got my voltage, I've got my power. So I can do V equals P equals, and what I want to figure out is I. Right? Is there an equation that is using those three? I think so. I think it's P equals VI. So if I rearrange that, I get I equals P over V. and then I substitute those values, and my current is 0.25 amps. Now, what I also want to figure out is the resistance. So R is my question mark. But I do know my current, and V equals IR. Using that equation, rearranging R equals VI, V over I, substituting in my values, and then I should get 960 ohms. So you really should be able to use all of those equations kind of conjunctively, and because you know so many facts. Alright, what about this one? How much electrical energy would a 240 volts? So that's a fact. V equals 240. Current is 10 amps. And time is 15 minutes, but we have to make sure you convert that to seconds. So 15 times 60, so I get 900 seconds. What am I trying to find? Well, it says how much electrical energy. So energy is what I'm trying to find. So delta E is what I'm trying to find. So how do I tackle this question? Well, first of all, I would have a look at all my power equation and see which one I can calculate power for. So power equals VI also equals to delta E over T. So what I can do is kind of ignore the P for now, because they should equal each other, and just rearrange these ones. Right? Delta E is delta VI times T. Okay, easy. So I'll substitute 240 in here, 10 amps in here, and then 900 seconds in here, and then I get a very big number. Cost of electrical energy. So now we're going to look at cost. So this is the next part. The amount of money paid to the energy provider is dependent on the total electrical energy used by the consumer and the time of day in which the energy was consumed. So you actually pay a different amount of money depending on what time of the day it is. An energy provider measures the consumption of electrical energy in units of kilowatt hours. 1 kilowatt hour, it's a bit a handful to say, is equal to 1 kilowatt of electrical power consumed in 1 hour. That makes sense. And is calculated using the formula below. So delta E equals P times T. So that's all here. So that's how much energy we use. So P times T. So I would copy that down. That's just rearranging P equals delta E over T. One of the equations we have already. The energy provider charges an amount of money per kilowatt hour of energy used by a consumer. The cost of electrical power is calculated by finding the product of the energy consumed and the cost per unit of energy consumed. Now, because we keep talking about kilowatt hour, you have to make sure your time, I know our SI unit is seconds, but in this case, when you use this equation, you have to make sure this time is in hours, because that's how we calculate it. Just the cost. I know we normally use SI units, but cost, when you think of cost, you make sure it's in hours. So basically, this is our equation. Cost is delta E times cost over delta E. So basically, cost is going to be how much energy we use times how much it is per energy we use, per energy unit. So it'll make more sense once we actually try a question. So, for example, light, power rating 50 watts, 25 hours, television 200 watts, 5 hours, iron 500 watts, 2 hours, and etc. So approximate time to use 1 kilowatt hour. These are all 1 kilowatt hour, and that's how much time you can use it for, because they're different power. Alright, so let's actually have a go at this one. So they use it for 3 hours. So I would put T as my 3 hours. Your price is 30 cents per kilowatt hour. So all you have to do is, first of all, write your power, 180 watts. And then I would write 0.18 times 10 to the power of 3 watts into kilowatts, because we want kilowatts. So that's important as well as also as having hours. So make sure it's in kilowatts. Time is 3 hours. My delta E is question mark, so I have to use that equation. Delta E equals PT. And then once it's in kilowatts and once it's in hours, you can just times them together and get the unit of kilowatt hours. If you don't get an answer that's kilowatt and hours, your answer unit won't be right. Basically, your answer won't be right. So 0.54 kilowatt hour. So now the cost is 37 cents. per 1 kilowatt hour. So they didn't use a whole 1 hour. They only used about a 50%. So it's only going to be approximately half of 37 cents. And to just figure that out, you just go 0.54 kilowatt hour times 37 cents. Right, so how much energy you used and how much cost it is per energy unit. All you have to do is just times that money together. It's like kind of saying 1 apple is $2. How much is it going to be if I buy 5 apples? All I have to do is just times how many apples I bought times how much it's going to be per apple. Alright, so hopefully you can understand that just comes by timesing the costs together. Alright, this one you should be able to do, so 120 watts. So what current will it draw? So I is the question mark, V I got, W I've got, so I should be able to do it. I might just get you guys to do these questions and we can talk about it. If you want me to, I can make videos on it, but you should be able to do all these pretty easily, so I'm going to leave you to it. You can help each other, but I'm going to move on to energy efficiency. Alright, efficiency is basically how much of the electrical energy gets converted into something we need. Right, so for a light bulb in case, we want it to turn into a light. But you hopefully understand that it also gets turned into heat as well. So light is something we like, that is useful, and heat is something that we don't like, so it's not very useful. So let's have a look. Energy efficiency is now a big issue with rising electrical costs in South Australia. The efficient use of lighting has undergone a renaissance in recent times with the transitions from the incandescent globe to halogens to fluoros to LED lightings. Now, incandescent globes are highly inefficient, meaning only 2.2% out of 100% of electrical energy is being converted into light. That's not much at all, with most of the energy actually going to a form of heat. However, so that's what we started off with in the beginning, in the olden days. Now we use LED, which converts about 20% of its energy. So it's almost 10 times higher than the incandescent globe. Although it's 20%, it's still not a lot compared to 100% it being converting, but it's the best we can do, and it's more efficient. So these equations is what we're going to be using. Now, if we can use useful output energy and total input energy, or you could talk about power and input and output power. So you could write both of those equations, because depending on what words they use in the question. So write those in your equation sheet. Okay, energy is transferred to components and loads by charged particles flowing in an electrical circuit. Components and loads then transform the energy supplied into different forms. Some forms of energy produced by a component or load are useful, and some others are wasted. So in a light bulb example, light is useful, heat is wasted. So so that's what they talk about. Wasted energy, to calculate wasted energy, you get total input energy and take the useful output energy, and that's how you find the wasted energy. So, as you can see, if 100 joules was the electrical energy that goes in, and light energy was 75 joules, then you just figure out 100 take 75 and get 25. If they gave you the heat energy and said find the light energy, then you would just go 100 take 25 and get 75. Right, let's do an example. An incandescent light bulb outputs 40 joules of light for every, so output is 40 joule, output energy, for every 1200 of energy supplied. So input energy is 1200 joules. What you have to do is calculate the efficiency of this light bulb. So output is 40 joules, input energy is 1200 joules, and efficiency is the question mark. So use that equation, efficiency percentage equals output divided by input times 100. So all you have to do is chuck that in the calculator and you get about 3.3%. Right, so I'll get you to do these ones. You should be able to do all these. Now this particular one is straight from your workbook. There's a worked example on page 72. If you want to go have a look at it, there's answers there. Same with this one. Same with this one. This one I haven't uploaded answers, but you should be able to do them. Give it a go. I feel like you should be fine with it. help each other. And basically that's all the content that we've got to learn for electrical circuits, guys. And I really want you to focus on getting it all done, making sure your PowerPoints are all done. And then we'll start with the revision, starting with the workbook questions, and then I will release a practice test soon. Alright, good luck.